So what we will do today is continue a little bit on the special topic of dynamics and nonlinear analysis. How many of you are actually using nonlinear analysis in your projects? Cannot, well, few, still few. So it'll be better, I think, if you know exactly what Abacus is doing behind the scenes when you're running some sort of a nonlinear analysis procedure. So what we were talking about last time was on this topic of dynamics and nonlinearity. And I showed you that when you have a dynamic problem, the equation of motion is given by this. This is the governing differential equation, which holds at every point everywhere in your domain. And if you use the familiar method of weighted residuals, all that you to do is to take your governing equation, multiply it with the virtual displacement, integrate by parts, take our finite element approximation, and I mentioned to you that the finite element approximation is the exact same thing, except now that your degrees of freedom are going to be functions of time. So these are nodal displacements, and if you take the second time derivative of that, that will give you a very similar formula for accelerations. So acceleration at any point in the domain can be found using the same type of shape functions that you used for displacements. And we saw that the only extra term that dynamics creates is this one. This is the inertia term, which leads to the mass matrix. And then finally, it leads to the familiar equation of motion for multi-degree of freedom systems. So hopefully, this is something that you should have seen before. So we said that now this is a second order ordinary differential equation, a system of second order ordinary differential equations. So to solve this, what we need to do is some sort of time integration methods. And we took a look at a simpler case first, which was heat conduction, a very similar equation that we get from heat conduction. Here this M is heat capacity matrix, K is the conductivity matrix, F is the heat source per point. So this is a transient heat conduction problem, meaning that it takes some time for the temperature to evolve into a steady state. So we saw that for these types of first order differential equations, one of the most common methods that we use is the Euler method. And Euler method, all that it basically does is it somehow approximates the derivative from one time step to the other. And we talked about how there are these different types of Euler methods. One is a forward Euler, where we choose alpha equal to 0. What that means is that we are assuming that the rate of change of temperature at this point is equal to this line. And when we integrate that, that takes us to this point. And we know that every time we do a time stepping procedure, we'll make some error. Similarly, if you use a backward Euler, what you're doing is you're approximating the derivative with this function. So if you start here and take this slope, that would take you somewhere here, down. And that again causes error. And then there is this midpoint rule, which says that, well, I'll take the average of the derivative at this point and derivative at this point. And that actually turns out to be a much better approximation for the derivative. So what you get here is a second order accurate method. What that means is that if you're taking all these time steps, and if you reduce the time step by half, your accuracy of D is going to go up by 4 times with this midpoint rule. But these two methods are first order accurate. So what that means is that if you reduce your time step by half, your accuracy will go up by 2. So these are basically the more common first order methods, the Euler method. And if you substitute these two equations into the into the matrix equation, then you can solve for rate of change of temperature. Everything here on the right hand side is known, and then you can take this Vn plus 1, go back here, calculate Vn plus alpha, and substitute in here, you get Dn plus 1. So again, the idea of time stepping was that you know the state of the system at some Tn, and you go using that state to the next Tn plus 1. So the same idea we sort of extended to structural dynamics, which was a second order differential equation. So one way was that we could convert this second order to a system of two first order equations. So what was the, is there some drawback to this? If we take our structural dynamics equation of motion, convert it to two first order systems. Now these two first order systems I can solve using my Euler method. But is there some drawback to this? Right, so we have just doubled the number of equations, which will take much more time to solve. There is an alternative called the Newmark family of integrators, where we are again just approximating the derivative, which is velocity and acceleration. So we are approximating the velocity at the next time step with this expression, which depends on gamma. We are approximating the displacement at the next time step with this expression, which is again something that you might be familiar with from dynamics. This is old displacement plus t times velocity plus half at square. And then if you plug those two equations into your matrix equation, then again you get this long expression where everything on the right hand side is known. Everything on the right hand side is, you know the load applied at the next time step, you know the previous or the current velocity, current acceleration, current displacement, velocity and acceleration. You know everything here, you can calculate the acceleration at the next time step. So right here, you know everything here, you can calculate A. Once you calculate A, you can plug that back into these two expressions and calculate V and D. So the state of the system at any instant is given by these three variables. So the two most common time stepping methods that people use, one is this central difference method. This is explicit, and this is exactly what Abacus Explicit uses. So how many of you have used or tried to use Abacus Explicit for your project? Okay, very few. So now this explicit is, by definition, you're solving a dynamic problem. But quite a lot of times people what they will do is use a very high damping and use it to solve static problems. So the idea is, like I was telling you last time, if you have a cantilever beam, you apply a sudden impact load on that, it will oscillate, and then it will reach its steady state. So with Abacus Explicit, if you use a large displacement or a large damping, then you can calculate the final static displacement as well. And the benefit of Abacus Explicit is that this is an explicit method. It does not have the types of convergence problems that implicit methods do. And one of the big reasons for that is that, take a look at this. Gamma is half, beta is 0. If you take those two expressions, plug them here, this term, beta is 0, goes away. So you can see that the displacement at the next step, if you start from here, you can calculate the displacement at the next step purely on the basis of what is known before. Does that make sense? You don't even need to calculate the acceleration at this time step. What Abacus Explicit does is it calculates the displacement at the next time step purely by projecting the displacement and velocity from the current time step to the next. Once you have the displacement there, you can go back and solve an and vn plus 1 using this equation itself. So the reason for this is also the reason that this is called an explicit method. Also because this matrix, beta is 0, this goes away, C is diagonal, M is diagonal, so your matrix itself is diagonal, and those types of methods are called explicit methods. Um, so those methods, you're not actually solving a system of equations. So they are very easy to converge. You're not iterating for your solution. And then the other method which Abacus standard uses for dynamic problems is this half and beta is equal to 1/4. The good thing about this method is that this is unconditionally stable, meaning that you can choose any large time step and it would, your solution would still be stable. It will not oscillate wildly. Your accuracy might not be very good, but at least it will be stable. So that was pretty much what we talked about in time integration. And then we briefly introduced this idea now for nonlinear problems. So I told you that usually nonlinearity in a model results either from material or geometric nonlinearity. And you might remember from the talk on Friday, there is another type of nonlinearity. What is that? Boundary. If your boundary conditions are changing, or like a contact boundary condition, something like you have a cantilever beam and you have a stop here, when it oscillates, it might hit the stop. So when your boundary conditions depend upon the displacement, that is also a type of nonlinearity. And some people consider that geometric nonlinearity, but just to be consistent with Abacus, maybe you should also consider material, geometric, and boundary nonlinearities. So this was, we talked about this Newton's method, or some people call it Newton-Raphson method for solving nonlinear problems. And I'll go over this a little bit, and then we'll do a little in-class exercise on this. So the idea is that you want to solve this nonlinear spring applied load with some applied load. You want to find out what is the U, what is the displacement if you apply load P. And the nature of this nonlinear spring is given like this. So we say that if you stretch it by U, the force that the resisting force that develops in the spring is given by K times U plus K1 times U cube. So this is clearly nonlinear. If it was a linear spring, this term would not be there. It would just be K naught times U. So the equivalent linear spring has this slope K naught that I've shown with the dotted line. So now, if you write out the equation of equilibrium, you'll see that internal force minus external force must be 0 to find out what is the value of U for a given load P. And the way we solve this equation, what is the first step for solving a nonlinear equation? You assume a solution, and once you assume the solution, you also try to calculate what is the derivative at this point. So for example, in this case, let's say this is the curve. If you take this curve and subtract P, I will get this G, this new curve. And solving this equation means that I'm trying to find where does this curve go to 0. This is basically what is happening in all nonlinear problems. And quite a lot of times, these nonlinear problems, this solution may not be unique. There may be multiple solutions, or there may not be any solution at all. So for nonlinear problems, you have to be very careful when you're running Abacus or any other finite element software. So the idea is that in this case, I'm going to assume that if I apply a load P, my spring is not going to displace at all. That's an initial assumption. I can assume anything I want. So if I assume that my spring is not going to deform at all, then my initial assumption is right here. And then the second step is you will use a Taylor series expansion. So you're going to try to find out how much delta U should you add so that the new solution should become closer to 0. And if you write this out in a Taylor series expansion, you will see that you get a GU, gradient of G times delta U, and there are other higher order terms, but we'll neglect that and say that this is equal to 0. And now this is an equation that you can solve for delta U. So, so people normally call this term right here, they call this term as a tangent stiffness. And what you do then is basically this tangent stiffness times delta U is equal to minus G. You can solve this for delta U. So what happens is this tangent stiffness, what it represents this slope. And let me actually zoom in here. Right, so what we have here is this was our initial assumption. This is the tangent stiffness. So given this tangent stiffness, it predicts that the solution should go to 0 at this point. And this distance from here to here, that is delta U. So now this becomes your new assumption, and you repeat the process again. So at this point, you calculate the value of G again, and you see that this is the value of G is not 0. And then you calculate the derivative at this point, and this derivative tells you that maybe G is 0 here. And then you see that G is not 0 here either, and you keep on repeating this process until you finally converge to this point. Now another thing to note here is that you will never actually hit the exact solution on the dot. So normally people use some kind of a tolerance, and that tolerance is sort of depicted by this circle here. Once your assumption reaches within this circle, then you say that I'm close enough to the solution, and I'll accept this as my solution. All right. So the in-class assignment that what I'd like you to do is we'll take this same spring and so our spring stiffness is given by K naught U plus K1 UQ. The equation that we are trying to solve is the internal force minus external force is equal to 0. My initial assumption is according to the linear. In this case, I'm going to assume that my solution, initial solution, U0 is equal to the initial, according to the linear problem. So that would be P divided by K naught. And the values that you can use for K naught is 1, K1 is 1, and the applied load P is 1. And the objective is, the final objective is to find U, but all I'm asking you to do is find the next iterate, find U1. So you have to go through this step once. You just have to find delta U and tell me what is the next assumption, what is the next solution that you would assume according to this Newton's method. So is the problem clear? So use these values and find out what is the next iterate. So essentially what I'm asking you to do is, you have assumed this as the solution, go to this point, calculate G, calculate gradient of G, and then you will come down to this point. And what is this point is what I'm asking you. All done? So those of you who are done, please can go ahead and pass it down the table here. All right, let's start handing it in, and then we'll talk about this. Done? All right, so let's see what this would be. So if you assume u0 to be equal to p over k naught, and plug in the values for p and k naught 1 and 1, u0 is 1. What is the value of g at this point? G at u0. No, that should be 1 plus 1 minus 1, which is 1. What is the value of the tangent stiffness? Tangent stiffness would be d, the gradient of g with respect to u. That is k naught plus 3 k1 u square. That is equal to 4. And that implies that k times delta u is equal to minus g. Implies delta u is equal to minus 1 over 4. And therefore, u1 is equal to u0 plus delta u, 1 minus 1 upon 4, 3 upon 4. So essentially what we have done here is, going back to this curve, we assumed that this was the solution. We calculate g at that point, calculate gradient of g at that point. That will take you down to this point. And you can keep on repeating this process until you hit this equilibrium point. So that is basically the essence of almost all nonlinear problems, all nonlinear solution methods. All nonlinear solution methods try to approximate this gradient somehow. Now, the beauty of this nonlinear, this Newton-Raphson method is that this is second order accurate. And what that means is that this convergence, as long as you are using this exact gradient, your convergence is going to be second order accurate. if your gradient is even a little bit off, this tangent stiffness matrix, if this tangent is even a little bit off, you immediately lose your second order convergence. So it will take a lot more iterations to converge to the exact solution. But if it's a Newton-Raphson method, if it is a consistent tangent, then you will get your solution generally converges within 5 or 6 iterations. When people use a tolerance something like as small as 10 to the power minus 6, so you can imagine that's a very small tolerance, and it will take it takes only 5 or 6 iterations to get down to that level of tolerance. That's a Newton-Raphson, consistent Newton-Raphson method. There are other methods which are modified Newton methods which do not display the second order accuracy. So essentially this is what is going on in nonlinear solution methods. And now this was for a simple single degree of freedom problem. What happens in a more complicated multi-degree of freedom system is something like this. Essentially what we are doing again is solving the equilibrium equation on the deformed configuration. So for example, what I'm showing you here is this cantilever beam. You apply some moment to it, and as you keep on increasing the magnitude of that moment, this will actually turn back on itself, and depending upon the material properties, it may turn into a perfect circle. So in this case, again, what you have are multiple different steps of the nonlinear analysis, in the sense that if you apply a small moment, your equilibrium configuration will be this. From here, if you apply additional moment, your equilibrium configuration will be this, and so on. So if you choose this equilibrium equation defined on that deformed configuration, you can write the same equation back on the original configuration in a little different way. So what you should note here is that this div sigma plus b, this is our favorite equation, but when you transform this equation back to the original configuration, it can be expressed as a big divergence of first Piola-Kirchhoff stress tensor plus a modified body force is equal to 0. So the equation is very similar, and I'll tell you what these terms are in a little bit. The main difference here is that this divergence is taken with respect to the original coordinates. This is the original configuration of the system. This is denoted by big X. This is the deformed configuration of the domain, and this is denoted by small x. So the derivatives in this equation are all with respect to the original configuration, which is a big deal because you don't even know the final configuration. You don't even know the final configuration, and you are being asked to calculate all the derivatives and all the integrals and everything on the final unknown configuration. So in order to solve these types of equations, what we do is we again take the equilibrium equation, multiply it with the virtual displacement, integrate over the domain. But at this very step, we will transform this integral from the deformed configuration back to the original configuration. Now this is something that we have done for isoparametric map also. In the isoparametric map, what we said that we will deform or we will transform this integral from the actual element back to the parent element. In this case, what we are saying is that we'll transform this integral from the deformed to the undeformed configuration, and when we do that, the familiar j, determinant of j, that comes and sits in here. And if you take this entire equation, this equation is nothing but the equilibrium equation on the undeformed configuration times the virtual displacement. Now what are all these quantities? So for large deformation problems, you should remember that we had defined this quantity f, that is deformation gradient, which is identity plus gradient of displacement, and this Jacobian, or the determinant of the Jacobian, this f is nothing but the Jacobian from the undeformed configuration to the deformed configuration. That's all that this f does. And this this first Piola-Kirchhoff stress tensor, you don't actually have to find out how, or this thing did not drop out of the sky or something. What people found was, if you transform this integral from the deformed configuration to the undeformed configuration, you will see that when you take this J inside, this P naturally comes out to be, this first Piola-Kirchhoff tensor naturally comes out to be J times Cauchy stress. This was our regular stress times F inverse transpose. And this first Piola-Kirchhoff stress tensor is not symmetric. You know that sigma is symmetric, right? But P is not symmetric. So to get a symmetric tensor in the undeformed configuration, if you just pre-multiply it with F inverse, this is called the second Piola-Kirchhoff stress tensor. So how many of you have actually seen this Piola-Kirchhoff stress tensor before? Okay, that's good. So, and this body force in the deformed configuration is this B or this B multiplied with determinant of J. So this is nothing but, all these terms come out very naturally from this integral if you just are consistent with your algebra. So after that, we already know what we want to do. Once we write out the weak form, we have to do integration by parts. And when you do the integration by parts, you are balancing the derivatives on the virtual displacement, and there is a real displacement sitting in P. So when you do that, what you get is F double dot with P. So what is double dot? What does double dot do? This F is a tensor, this P is a tensor. Double dot is is the element-wise multiplication of F and P, right? F is a 3 cross 3 matrix, P is a 3 cross 3 matrix. You take each element, the corresponding elements of those two matrices, multiply them and add them. That's double dot. And that is basically the internal virtual work. So another thing to sort of remember here is that in the linear problems, what we used to have was virtual strain multiplied with real stress. And for large deformation problems, what we have is virtual deformation gradient multiplied with real Piola-Kirchhoff stress. And another way to write the same thing is this green strain. This green strain was nothing but this. If you consider the full strain, then what you get is the green strain, and times the second Piola-Kirchhoff. So this thing is exactly equal to this. And this is basically your weak form for large deformation problems. So when you discretize and use your finite element approximation, we are just using the exact same thing that we did for linear problems. U is equal to N times D. And the green strain, if you remember from the linear problems, it was used to be B times D. Here also we get something similar, B times D, but this B matrix is a little more complicated because you have to take care of that higher order quadratic terms. So essentially, when you substitute your finite element approximation, what you get is internal force minus external force is equal to 0. This is exactly what we had before in the nonlinear spring problem. Ku minus P is equal to 0. This term is like K of U. This term is like P. And in general, this external force can also be dependent on the deformation. Can somebody give me an example of what type of problem would you have when the external force, the applied force, depends upon your deformation? Sorry? Well, yeah, but that is internal force. The spring force is the internal force. I'm saying the applied load. The applied load also might depend upon the displacement. When can that happen? So actually, there are problems like hydrostatic problems for submarines, where the pressure is always normal to the surface of the submarine. If the submarine bends or flexes, the pressure changes according to the current configuration of the submarine. So the applied pressure, the external force, is also, in general, a function of your displacement. So essentially all you're doing is you're solving a nonlinear system of equations. That's all that you're doing when you're solving these nonlinear problems. And instead of a scalar equation, you will have a vector equation. So what is the term, let's say if this problem was linear, what would F internal be? This is something that we have done before for the linear problem. What was F internal when we were doing the linear problems? K times D, K times D minus F, KD minus F. That was our linear, for the linear problems. For nonlinear problems, internal force is a function of displacement. External force could, in general, also be a function of displacement. So, and then in order to solve these set of vector equations, we solve them in a very similar way to our single degree of freedom problem that you just did. You calculate the tangent matrix, which is derivative of this G with respect to D. And that in general is going to be a matrix. Because right now in your case, when you took derivative of G, that was a scalar. It was a 1 cross 1 matrix. In general, when you have a vector equation, you are going to get a matrix for the derivative, for the tangent stiffness. And that tangent stiffness can be again assembled element-wise. And the element stiffness matrix, you can see that where all these terms are coming from. This is the element stiffness matrix. If you just take the derivative of this with respect to the displacement, what you get is B transpose D B. So this thing is very similar to your B matrix. And this part of the matrix, or this part of the stiffness matrix, is called the material tangent. Similarly, there is a slightly different part of the stiffness matrix. Why? Because this B is not constant anymore. So when you take the derivative of this with respect to displacement, you get initial terms also, not this B, but there is a B transpose gradient of U sitting in this. So now this term is called the geometric stiffness. This term comes in because your structure has deformed and it changes its stiffness because of the deformation. That's the geometric stiffness. So for example, what you can think of is, let's say you have a trampoline or maybe a rope. You are holding that rope with almost zero tension, like this. If you stand on the rope, that will have a large deformation. If you now stretch the rope and stand on it again, it will not go down that much, right? So the stiffness of that rope depends upon how much internal force it's already carrying or how much deformation it has already had. So that component, this is the P delta effect that people talk about. And in general, since your external force can also be dependent upon displacement, you will have some term into your stiffness matrix that comes from the load. So the stiffness matrix has three components. One is a material, which is very similar to B transpose DB. This was our old stiffness matrix. You have two additional components. One is a geometric, and one is due to the load. So this is basically how Abacus or any other finite element software also solves these types of problems. And the steps for the Newton method are pretty much exactly the same, except what you can also do for these large deformation problems is that instead of applying the entire load all at once, let's say you want to apply this much load somewhere here. Instead of applying all that load all at once, it is better to apply it in small steps. So you can take your Newton loop. This was the Newton loop that we had before. Assume a solution, calculate G and all that. And you can put that entire thing inside a bigger loop. And all that loop does is steps the load by small amounts. Um, so So once again, you can see that for this type of a problem, you can have multiple solutions for this amount of load. So you have to sort of keep a track of where was your last converged point, and if you're increasing the load, you might have to do something like this. So just to give you an example of this type of a problem, let me pull up something from one of my codes. So this problem is, this is a cantilever beam. Um, it is fixed on the left end, but it is not fixed completely. It has a soft spring sitting here, and what I'm doing on the right end is applying a moment. So as I increase the moment, this thing will twist back on itself, and it will show you the nonlinear snap behavior. So let's see if we can run this. Um, I think I'm connected to the. Oh, so I guess I won't be able to run it. It's not connected to my system in my office. So anyway, so what this looks like is somewhat like this. Um, you keep on applying the load here, and finally this beam turns around on itself, and what you get this type of a load deformation behavior, and ultimately you see that the load goes up and then comes down, and when the load comes down, all those points are unstable. What that means is it's still in equilibrium, but that equilibrium configuration is unstable. So because the stiffness during all those steps is negative. All right, so just to briefly mention some of these things from Abacus. You've seen the sources of nonlinearity, and if you are using nonlinear problem for your project, you should maybe take a look at this. This 8.2.3 is the section which talks about how what are all these, what types of incrementation techniques does Abacus use. So what those incrementation techniques are these. How does Abacus decide how big a step to choose, and how close these points should be, how many times should it iterate, those kinds of things. So, and another thing, I think, if you for those of you who might be doing that lap joint problem, there is already an example file in this manual. So have you taken, how many of you are doing the lap joint problem? Have you taken a look at this? Okay. So there's already an example like this, which would also be useful for those of you who are not doing this problem, but somewhat a related problem. Anyway, so I guess we'll call it a day, and then next time we'll go back to beam theory.